Hi everyone, so this video is now going to be the first video covering the new material from chapter 4, tensor calculus. So please make sure going into this chapter that all the important points from chapter 1, which I revised in the last video, please make sure that you have all of that stuff at your fingertips. Okay, so make sure you have a good firm grasp on that, because as we go into this chapter, we're going to be using those transformation rules, we're going to be using the metric tensor, left, right and center. So we're going to be using those things all the time. So you need to make sure you've got a good firm grasp on them. And I think it's also worth saying that, at least initially, this chapter is quite dense. So it is quite theoretical, very abstract. So just kind of try to bear with it, okay? I will try to do as many examples as I can going through, but just by its nature, it is very abstract. It may not be clear at times what really the point is or what's the end goal of what we're doing. At the end of the day, it will all be justified when we get to the general relativity chapter at the end. So that's what we're working towards here. But in this chapter, we just want to build up the maths that we need before we get to the physics of the relativity. So it is very abstract. It's probably the most abstract maths that you're going to see in any AMA module, and I even include level 4 ones. So just try and go with it, and re-watch the videos if you need to, read your notes, and hopefully it will gradually become clear. So this chapter is called Tensor Calculus, as opposed to chapter 1, which was called Tensor Algebra. And the word calculus, hopefully, when you hear it, you immediately think of differentiation, integration, and that's exactly what we're going to think about here. So we're going to start out by thinking about what happens when we take a vector field, okay, which we've seen in chapter 1. A vector is just a special type of tensor. It's a rank 1 tensor. So we're going to take a vector and see what happens when we differentiate it. So let's suppose I have some vector, let's call it a capital T. And let's just start this off with an example. So imagine I have a vector field and it's just in 3-dimensional Cartesian coordinates. So maybe it could be something like this. So 2x times I hat plus 3x minus y over 2 plus z squared j hat plus z minus y k hat. Okay, so just a familiar vector field in 3-dimensional Cartesian coordinates. Okay, and vector field, the word field here means this vector is a function of position. Okay, so at each point in 3D space, this formula gives you a vector. And okay, so let's just see what happens if we try to differentiate this vector field with respect to one of the coordinates. Okay, so it can be x, y, or z. Let's go with z, why not? So the partial of t with respect to z will be as follows. So if I differentiate 2x with respect to z, I get nothing. So I get nothing there. And then moving over here, I will get 2z times j. And then over here, I will get plus z. Okay. Okay, that's it. Nothing very profound there. But what I want you to notice is how I did that. So whenever I differentiated this vector field, what I did was I just differentiated it component by component. Okay, so I differentiated the x component. Okay, so in other words, the coefficient of I hat, and I got 0. And then I differentiated the coefficient of j hat, and there it is there. And then I differentiated the coefficient of k hat, and there it is there. Okay, so the coefficients of the unit vectors. Now, the reason I am allowed to do that is because these unit vectors here, well, it's not important that they're unit vectors, but these basis vectors, I hat, j hat, k hat, they are constant. Okay, they're constant. What do I mean by that? I mean, no matter where you are in three-dimensional space, the vectors I hat, j hat, and k hat are always the same. Okay, so they always have a unit length and they always point in the same directions. Okay, so no matter where you are in space, I hat, j hat, and k hat, they don't depend on position. Okay, they're always the same. And that is what allows me to differentiate this vector field component by component and just keep the basis vectors as they are. Okay, so notice, you know, strictly speaking, if I go to differentiate this, right, I have to use the product rule here. Okay, I've got 2x, which I differentiated and got 0 with respect to z, but then you should also use product rule and you differentiate the basis vector too. Okay, so you may not even have thought of that, but the reason it's not a problem here and that we don't have to do it is because it's just a constant. So when you differentiate any of the basis vectors, you would get 0. Oh, that's a bit smudgy. Oh well. But here's the rub. That only works in Cartesian coordinates. So if you go to a different coordinate system, so for example, let's go to two-dimensional polar coordinates, let's say for example. So imagine I have the 2D plane. Okay, so here's x and y, so those are the Cartesian coordinates. And as I say, to make it clear, you know, if I pick any point, then I hat and j hat are always the same. So at that point, there's I hat and j hat. And if I pick a different point down here, here's I hat and j hat. But if I instead use different coordinates, so let's go for polar coordinates, then what we will see is that the basis vectors do vary from point to point. Okay, so for example, if I take this point again, and let's just draw a little dotted line out to it, then the basis vector for the r coordinate, so e subscript r, will point in that direction, and e theta will point in this direction. Okay, the direction of increasing angle. Okay, so that's the basis vectors point in the direction of increasing coordinate. So ER points radially out and E theta points in the direction of increasing angle. Okay, so that's how they look at that point. But if I went to this point down here, they're totally different. Okay, so ER will be like this and E theta will be like that. Okay, totally different. Okay, they're pointing in totally different directions. Okay, totally different vectors. So if, going back to this now, if we had a vector that was expressed in a general coordinate system that may not be Cartesian, then when we go to differentiate with respect to one of the coordinates, we must account for the fact that the basis vectors vary with position, and so they need to be differentiated too. So let's now approach that formally and see how that's done. Okay, so let's imagine now, completely in general, we have some vector field, and again let's call it capital T, and let's express it in terms of components and basis vectors. Now, again, there are two ways of doing this, so you can write the vector field in contravariant form or in the covariant form. So here, let's go with the contravariant form. Okay, so this vector field T can be written as T superscript j, so the contravariant components, times ej, the natural basis vector, sum over j. Okay, Einstein convention, Einstein summation convention. Okay, and let's see what happens now if we go to take the partial of t with respect to one of the coordinates. Okay, so let's say coordinate xi. Well, that's just d by dxi of this, so tj, ej, and now we have to use the product rule. So, in the first term, let's differentiate the tj, so dtj by dxi, times ej. And then in the second term, let's do it the other way around. So we have plus tj dej by dxi. Okay, and as I say, in general coordinates, this term will be non-zero. Okay, so the derivative of the basis vector with respect to the coordinate. Okay, in general, that can be non-zero. So how do we find it? Okay, or where do we go from here? Well, what you should bear in mind here is that when I differentiate a vector, I expect to get as my answer another vector. Okay, so in the example I did a moment ago, where it was in Cartesian coordinates, I had a vector field in Cartesians, and when I differentiated it with respect to z, I got something else, but it was still a vector, right? It was another vector field. And that is still the case here. Okay, so this derivative of the basis vector ej with respect to xi, what it is exactly, I don't know. Okay, so don't know what it is, but this is a vector in its own right. Okay, so I will say dej by dxi is a vector in its own right. And so because it's a vector in its own right, it can be written in this kind of form. Okay, so this is a vector in its own right. It has components and basis vectors, right? So this vector can be written as a linear combination of components times basis vectors. So I'll say, so we can write it as follows. dej by dxi equals, so we'll have some basis vectors, okay, and we need to use a new letter k, and then the components, I am going to use the symbol capital gamma to denote them, okay, so I'm going to put a gamma with a capital K here. Okay, so sum over k, once again, all right, Einstein summation convention. And because here on the left-hand side, I have got two downstairs indices, okay, I and j, I will also put I and j here. Okay, so this is a vector in its own right, and this is just this vector written as an expansion over the basis vectors. Okay, so sum over k, and these gammas are just the expansion coefficients, that's all they are. And there's a very special name for them. They're called Christoffel symbols. More specifically, they're called Christoffel symbols of the second kind. Sometimes they're also called connection coefficients, or even just the connection. Sometimes it's just called the connection, but that's what they're called. Okay, fine. So let's take this formula. Now we still don't know how to find these Christoffel symbols. Okay, we haven't got a formula for them or a recipe for them, not as yet. But anyway, just for now, let's take this and put it back in here. Okay, so let's go back to this equation. So the derivative of the vector field t with respect to coordinate xi, and let's now put in here for this derivative the expansion of it with the Christoffel symbols and the basis vectors. So this will become, so the first term stays the same, so dtj by dxi ej plus tj, okay, and then dej by dxi is gamma k I j e k. And doing this actually allows me to combine these two terms together. Okay, because if you look carefully, you'll see that in the first term, you've got a dummy index j, here and here, and in the second term, you've got a dummy index k, here and here. So what I'm going to do is, in the first term, I'm going to change that j into a k. And then this will become basis vector ek, which we also have here, so it can be factored out. So we will have dtk by dxi plus, and then the second term we don't change, so but I'll write the Christoffel symbol first, so I'll write the kij here, and then the tj after ek. Okay, so all I've done there is just in the first term, change the dummy index j into a k, and then I factored out ek. And so now what we have got here is a recipe or a formula for how to differentiate a vector field t with respect to one of the coordinates. Okay, so if you differentiate a vector field t with respect to one of the coordinates, you get another vector. Okay, so as I said, you differentiate a vector field, you just get another vector field, and this is it here. Okay, so this is the component of that vector field. Okay, so these things here are the components of the vector field. Okay, so this vector field, and these are the basis vectors. Okay, so these, I'll just write, these are the components of the vector field, dt by dxi. Specifically, they are the contravariant components. Okay, because this is a natural basis vector, so the thing in front is the contravariant component. And there's actually a special notation for this. Okay, so the special notation is like this. So this object here, which I'll copy again, so this component, so dtk by dxi plus gamma kij tj, it's denoted nabla I T K. And there's also a special name for it. It's called the covariant derivative of tk with respect to xi. Okay, so this is a recipe for how to differentiate a vector field. You just take its contravariant components, so the tk's, and then this is what you do. So you take, first of all, just the usual partial derivative with respect to xi of that component, but then you have to add this extra term here. So Christoffel symbol times the components of t with a sum here over j. So that is the answer for how you differentiate a vector field. But there's one crucial piece of information that's missing, and it's about the Christoffel symbols. How do you find them? Right? So if you're given a coordinate system, how do you find these Christoffel symbols? So that's the last thing we'll write down now before the end of the video. Okay, so last thing we need to know to be able to differentiate a vector field, so to be able to find those covariant derivatives, is how to find the Christoffel symbols. Okay, so remember what the Christoffel symbol is. It's something that's obtained when you take a basis vector and you differentiate it with respect to one of the coordinates. Okay, and as I said earlier, differentiating a basis vector just gives you another vector. So this new vector can itself be expanded in terms of the basis vectors. And that's exactly what the Christoffel symbols are. They're just the expansion coefficients. And to figure out how to find these expansion coefficients, what we do is we take this equation and we just take a dot product on both sides of it with a reciprocal basis vector. Okay, so let's take a dot product with E superscript m. So dej by dxi dot product E superscript m is equal to gamma kij ek dot E superscript m. And as you will hopefully remember from the definition of reciprocal basis vectors, this thing, so E subscript k dot E superscript m, is nothing other than delta m k. So in fact, in the sum over k here, you have only one non-zero term, which is when k equals m. So this is nothing other than gamma m I j. So that is the formula for how you find Christoffel symbols. Okay, so to do it, you need to know what your natural basis vectors are for your coordinate system. You need to know what your reciprocal basis vectors are for your coordinate system. You need to be able to take this derivative, which may or may not be so straightforward. Okay, it's straightforward if you know how to express these basis vectors in terms of the Cartesian basis vectors. But at any rate, in general, in principle, this is how it's done. And I say in principle because in reality, we will never do it this way. Okay, so to do it like this is very difficult, and the algebra can become very, very messy very quickly. So, well, you will have some practice at it on your homeworks, but it's not the easiest way to find the Christoffel symbols. So in the next few videos, we're going to study the Christoffel symbols in much more detail. We're going to look at their properties, but we're going to find a couple of other ways of finding them.